Hi. So in this question, we are going to look at this special integral, and this integral is 0 to infinity e power minus y square dy. And you will find this integral in higher maths in normal probability distributions and so on. And it's a very useful integral. However, what I want you to see today is how we find the value of this integral using standard methods that even someone in high school or in grade 11th or 12th can understand. And specifically, we will be looking at how to prove that this is equal to root pi by 2 by using the Newton-Leibniz differentiation method. So as you might have understood already, like this is a way to differentiate an integral. So if you have something like this, f of t dt and hx and gx, then this comes out to be a function of x, and we know how to differentiate this. P dash x is basically f of h of x, h dash x minus f of g of x, g dash x. So this is the Newton-Leibniz method of differentiating an integral. And we are going to show you a nice way by which you use this to get the proof of this integral, right? So let's get started. We start by defining a new function, g of t. And let's call this new function g of t as integral of 0 to t e power minus y square dy and the whole square of this, right? This is my new function. So think about it. What is g of infinity? G of infinity is basically 0 to infinity e power minus y square dy whole square, right? Correct. And what I want to find out is actually root of g of infinity, right? Root of g of infinity will simply be 0 to infinity e power minus y square dy, right? So ultimately my objective is to find root of g of infinity, right? So how do I do that? So we have taken this function. Now what we will do is basically differentiate this g of t using the Newton-Leibniz method. So we can say dg by dt. How do I do this? So by chain rule, you can write it as twice of integral 0 to t e power minus y square dy, and then multiply it by the derivative of this integral, which will be e power minus t square and differentiation of t minus e power minus 0 and differentiation of 0, which will become 0, right? So this is coming out to be dg by dt is becoming twice of 0 to t e power minus y square dy multiplied by e power minus t square, because the derivative of t is 1, right? So this is my first expression. Now what I can do here is I'll realize that this integral is an integral over the variable y, right? So if it's an integral over the variable y, t is a constant for that, and I can take t inside the integral. So basically what I'm saying is I can write it as 0 to t e power minus y square multiplied by e power minus t square dy, right? That makes sense because this is a variable that is not the variable of integration, so it can come out. So if it can come out, it can go in, right? So this is the expression right now that we have. So we write it as dg by dt is equal to twice of basically integral 0 to t e power minus t square plus y square dy, correct? Now, the next step in the process is a change of variable. So what is the change of variable that we'll try to do here? We'll say x is equal to y by t. If x is equal to y by t, dx is equal to 1 by t dy. So therefore, dy is equal to t dx. And also the limits will change because y was going from 0 to t. So x will go from 0 to 1, right? That is obvious. So this becomes twice of 0 to 1 e power minus t square plus y square becomes x square t square, and this becomes t dx, right? I have replaced all the terms. I have replaced dy, I have replaced y, and I have changed the limits. So this becomes integral 0 to 1 2t e power minus t square common 1 plus x square dx, right? This is my dg by dt. So keep that in mind. This is my expression for dg by dt that has come right now. Now, what do I do at this stage? What I will do is notice that this is a derivative of some function, right? So what is the function? If you think about the function minus of e power minus 1 plus x square t square divided by 1 plus x square, and I try to do a partial derivative with respect to t here, right? So if I do a partial derivative with respect to t, what will I do? Minus, I'll keep it as it is on top, 1 plus x square t square, and then multiply by the derivative of the top part, but I'm doing derivative with respect to t, so I should get minus 1 plus x square, and then I will get a 2t, right? And then there is a divided by 1 plus x square, which acts as a constant. So this gets cancelled here, and minus minus becomes plus. So this becomes 2t e power minus 1 plus x square t square, right? So you can notice that the partial derivative of this function is equal to this, and this was in my integral earlier, right? So we can say that dg by dt, which was earlier equal to 0 to 1, 2t e power minus x t square 1 plus x square, and this was a dx. This is equal to 0 to 1 partial derivative of minus of e power minus 1 plus x square t square divided by 1 plus x square, and whole is with dx, right? This is the crucial step in the problem. Since we have written it like a partial derivative, I can take that derivative sign outside and take the minus along with it. And I say minus d by dt integral 0 to 1. It is e power minus 1 plus x square t square divided by 1 plus x square dx. And that should be equal to dg by dt, right? I hope everybody has understood what we are doing. We have noticed that the derivative of this function is this, and then we replace this integral with that derivative, and we have taken the derivative sign outside with a negative sign, and we are basically getting dg by dt is equal to minus d by dt something, right? So that is a very simple differential equation. If somebody says dg by dt is equal to minus d by dt of some function, obviously g should be equal to minus of f of x, right? When you integrate, g will come out as minus of f of x plus c, right? So here, what we are getting from this, the next step is integrating both sides with respect to time. We get g of t is equal to minus of 0 to 1 e power minus 1 plus x square t square dx divided by 1 plus x square plus a constant, right? Why did I put a constant? Because once you integrate, you should get an arbitrary constant. How do I find this constant? I can use my earlier definition. My g of t, if you remember, was integral 0 to t e power minus y square dy whole square. So that tells us that g of 0 must be 0, because you put limit 0 here, the integral vanishes. So if g of 0 is 0, I'll put t is equal to 0 here. So g of 0 is equal to minus 0 to 1. And if I put t is equal to 0, the top part here vanishes. It becomes 1 by 1 plus x square dx plus c. And this integral is fairly straightforward. This becomes tan inverse x from 0 to 1, negative sign plus c. And that is minus of pi by 4 plus c. And this was g of 0 was 0, so 0. So therefore, we get c is equal to pi by 4, right? If c is equal to pi by 4, now my g of t function has become g of t is equal to basically minus of 0 to 1 e power minus 1 plus x square t square divided by 1 plus x square dx plus pi by 4, right? And if you recall, earlier we had said we wanted to find out root of g infinity. Root of g infinity was my 0 to infinity e power minus y square dy, right? So here if I take limit t tends to infinity, I will get g of infinity should be minus 0 to 1. What happens when I put t tends to infinity in the numerator here? If t tends to infinity, we get e power this thing will tend to 0, right? So e power this thing tends to 0, 0 dx. Why? Because e power minus 1 plus x square into infinity is tending to 0, right? So 0 dx plus pi by 4, and that implies that g of infinity is basically pi by 4, and therefore root g of infinity for me becomes root pi by 2, right? And if root pi by 2 is coming, we have proved now that 0 to infinity e power minus y square dy, which was root of g of infinity, has become root pi by 2. Now, this proof is obviously using Newton-Leibniz method and using some tricky substitutions that might not be apparent. Obviously, that is not something that you can discover on your own very easily. However, you have to understand that the way to prove this, there are ways to prove this without the method that I have just shown. But I wanted to show this method because it is accessible to anyone who has done 11th and 12th grade maths and a little bit of calculus, right? So there are other ways which involve a change of variable and going to a 3D version and spherical coordinates. That method is very simple, but you need a little bit of knowledge of multivariable calculus for that. The point of this video is understanding that this can be derived by elementary principles. And also in future videos, I'll be using this result to show you some astonishing and beautiful results from the theory of gamma functions. So I'll be making a series of videos on gamma functions, and I think you will enjoy those videos. So please stay tuned. We'll be using this result in the derivations there. So I wanted to lay the groundwork a little bit here. Stay tuned for more videos. If you like the channel, please subscribe, like the video. Also, share. There is a link where you can share your doubts on your issues and topics that you need help in, and you can send it to me on through the Google form link, and I will try and make content around that as soon as possible. See you next time.